turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. Coming up, the US record their first human death from bird flu. So should we be concerned? Also, a new drug to treat drug-resistant prostate cancer. And what have the Romans ever done for us? Well, apparently, widespread lead pollution.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Up first this week, the United States have recorded their first human death from bird flu. The patient, who did have underlying health conditions, was taken to a hospital in Louisiana after contracting the H5N1 virus, but they deteriorated. The infection is now spreading in cows, and it's even killing domestic and wild cats. So what's the risk for us? To find out more, we put in a call to Ed Hutchinson at the MRC University of Glasgow Centre for Virus Research.
We've been concerned about H5N1 bird flu for about 25 years now. It's a virus which is capable of causing severe disease in humans as well as spreading in birds. But it's become a real issue in recent years where a new strain of H5N1 has started spreading really aggressively around the world through birds, starting in Asia and then through into Europe, Africa, North America, South America, Antarctica. So it's everywhere now. It's caused enormous problems for wild birds, but it's also been very good at jumping from those birds into other species, particularly into mammals. And the most surprising case of that so far has been in the United States, where it's not only infected dairy cows, but it's become a dairy cow virus. It's fully adapted to spreading among cattle, and there's now this big outbreak of H5N1 in cattle in the US.
And when it gets into a cow, does it behave like it does in the bird? Or does it behave more like mammalian flu, the kind of flu that you and I get, a runny nose, sore eyes and high temperature?
So this was a real surprise to virologists. The first surprise was that cows got infected at all, because up to this point we would have said that cattle, for whatever reason, didn't tend to get influenza A infections. But the second surprise was the way it spread. The main thing it's doing in these dairy cows is it's infecting the udders and it's being shed in the milk. And it's being shed in the milk at incredibly high levels. Now, if you pasteurize milk, that kills the virus, so that's good news. But if you don't, the milk remains infectious, and that seems to be a good part of how it's spreading among these cattle now.
And what are the implications for people then? Are we worried that the cows might act as an interface, enabling the infection
Absolutely.
to jump more efficiently to us?
Yeah, so against the backdrop of the fact that the virus is still circulating in birds, within cattle, these are animals which are obviously farmed in large numbers, so you have 2 points of contact. You have people who are working with the cattle, you have dairy workers, and if you can imagine a big dairy, there's lots of opportunities for coming into contact with milk from these cattle there. The other is consumption of unpasteurized dairy products. There's a subculture of drinking what's called raw milk, so unpasteurized milk. We pasteurize milk for good reasons for killing all sorts of pathogens, and this adds another one to the mix. So we are concerned that both humans and domesticated animals like pets could be exposed to the virus that way.
And have there been many human cases via those routes?
It's unclear at the moment whether there have been human cases from the consumption of raw milk, but there have definitely been cases from occupational exposure in dairies. So these have generally been conjunctivitis, so people getting pink eye, probably from the milk coming into the eyes, some also respiratory infections. And there have been cases where farm cats have died almost certainly because they've been lapping up milk around the dairy. What we've also seen in the US and Canada have been 2 really severe cases of human infection, both of which put people in hospital, one of which sadly recently resulted in the patient dying. But these cases did not come from cattle. These came directly from viruses in birds. And we can tell that because the viruses they got are much more closely related to the viruses still in birds than to the viruses which are in cows. So this highlights the fact that we've now got 2 different places to look when we're thinking about risks of H5N1 infection of humans.
Does this not nevertheless put us on alert that this particular virus, this particular form of H5, appears to be quite good at getting into a range of mammals? of which we're obviously a member of that group of animals, and this might be the first steps towards a full incursion of this becoming a human flu.
It absolutely does. And there are plenty of reasons to be worried about the animals themselves from an ecological perspective and animal welfare perspective. But if we're just going to look at humans for now, adapting to a new species is a really difficult thing for a virus to do, but flu is unusually good at it. And it's good for two reasons. One is that it can mutate really quickly, and we could see signs of that in those two really severe human cases. But the other thing to be concerned about is that influenza viruses can breed with each other. They can swap genes back and forth between them if two different viruses infect someone at the same time. And we're currently in the middle of the winter flu season in the US. There are loads of people being infected with influenza viruses, which are already very good at infecting humans. And there is this risk that you could have an H5N1 virus swapping genes with a virus which is already good at growing humans and getting a head start to becoming a human virus that way.
So you end up with a kind of hybrid virus that looks like H5N1, something we don't recognise as a human population. We've never seen that before, but it's got the inner workings of a human flu that knows really well how to grow in our cells and to grow really efficiently and spread really well.
That's absolutely right. And most of the influenza pandemics we've seen over the last century have occurred that way. Most recently, the 2009 swine flu outbreak occurred by different influenza viruses breeding with each other.
What then should public health officials, doctors, etc. be doing to A, keep an eye on that, and B, minimise the risk?
The most important thing you can do is to keep an eye on it, because at the moment, there is not any evidence for human-to-human transmission. So we're not talking about a human outbreak right now. What we're talking about is the need to minimise the risk of the virus figuring out how to do that. So that involves minimising the chances of the virus learning its way around humans. So what does that involve? It involves biosecurity measures. So if you have farmed animals, trying to reduce the risk of them getting infected. If you're working with animals which could be infected, both monitoring and wearing appropriate PPE. And this is legitimately quite a challenging thing to do in big complex farms, but it's important that this is considered. I'm also very concerned, as lots of people are, by raw milk consumption in areas where H5N1 is spreading.
What about vaccines? They're our mainstay for preventing seasonal flu. Have we got vaccines that will combat this form of H5? And have we got them at the sort of scale it would take if this suddenly does start to take off?
So this is a kind of partial good news story. We know how to make influenza vaccines, and we also already have produced H5N1 vaccines. Indeed, the UK government has recently purchased an initial batch of vaccines for exactly that reason. What's also good news is that you don't have to have a precisely matched H5 vaccine to get some protection against a virus. Even if it doesn't give you complete protection, it might reduce the risk of severe symptoms or reduce the risk of you spreading it to other people. And this is very similar to what happens with seasonal influenza vaccines and why it's always worth getting them, even if they're not going to completely protect you against every risk of infection.
Ed Hutchinson there from the MRC University of Glasgow Centre for Virus Research. New model predictions suggest that Earth's subsurface might hold billions of tonnes of natural hydrogen. Hydrogen's one of the most abundant elements in the universe, and it can be a source of carbon-free energy too. Burning it releases mostly water after all. But teasing it apart from natural compounds that contain it, like water or natural gas, can be both expensive and carry a carbon cost, which has been a deterrent to the wide-scale adoption of hydrogen previously. But geoscientists think that there might be vast reservoirs of the gas trapped literally beneath our feet, and a lot of it within relatively easy reach. If they're right, their findings suggest that geologic hydrogen could produce twice as much energy as all of the proven natural gas reserves we still have on Earth. I've been speaking to Jeff Ellis at the US Geological Survey.
So we had generally assumed that natural accumulations of hydrogen just couldn't form because it's a very small molecule and it's very diffusive. It leaks out through rocks in the subsurface, and it's also readily consumed by microorganisms. But there was an accidental discovery of an accumulation of almost pure hydrogen gas about a dozen years ago in the country of Mali in West Africa. And as I learned about this discovery, and I started to question this notion that maybe we could form accumulations of natural hydrogen.
And presumably, if we were to go burrowing after hydrogen like that, it's not got the same implications as to dig up fossil fuels, petroleum, coal, gas, because there isn't a carbon footprint apart from the extraction process associated with it. So it would be a clean form of, I suppose, fossil fuel.
That's exactly right. And today, the hydrogen that we get is actually predominantly made from fossil fuels. In the process of making a kilogram of hydrogen, we actually release about 10 kilograms of CO2 into the atmosphere.
I suppose we should point out that there are, of course, ways of making hydrogen in a non-carbon releasing way. That is, if you use a sustainable energy source to do it. But that is the drop in the ocean compared to where most comes from, isn't it?
That's right. Today, very little of this clean hydrogen is being made. The technologies that we have do exist, but they're quite expensive. It's not really clear how we're going to get all this low carbon hydrogen that we think we're going to need.
How have you turned this into a tractable question/problem then?
We looked at what we do know about natural occurrence of hydrogen on Earth. This is something that has been studied for many, many decades, mostly by biologists that are interested in the deep biosphere and life on other planets. And we know that there are microorganisms that are living on hydrogen in the subsurface. Then there were some knowledge gaps that we had to fill in. And so we used analogs from other things that have been well studied, things like petroleum systems. So through studies of petroleum, we know how gases migrate and trap and get accumulated in the subsurface. And so we were able to then borrow knowledge from those fields to fill in gaps, to put together a global model of just how much hydrogen might actually be trapped in accumulations in the entire Earth's crust.
Before we come to how much, just tell us where then we would anticipate this hydrogen might be.
The processes that are thought to be capable of generating the largest amounts of hydrogen tend to be associated with crystalline rock settings. Iron-rich rocks that are associated with the mantle underneath the Earth's crust that have been brought up near the surface, and also radioactive rocks. The radioactive decay of radiogenic minerals can actually split water and generate hydrogen. Actually, at the mid-ocean ridges today, we see the seawater being reduced and forming hydrogen. And also in many hydrothermal systems, hot springs and so forth, we find hydrogen gases there. And these are, by the way, very different places from where we explore for oil and gas. So this can explain why we don't find hydrogen associated with petroleum.
And they're also, by the sound of it, within reach, some of these sources, potentially.
Yes, absolutely. And in fact, this accidental discovery in Mali was only 100 meters below the surface. So in fact, it's very possible that it could be very accessible.
Now, notwithstanding the fact this is a model, therefore it's got strengths and weaknesses. There are going to be knowns, there are going to be unknowns. How much hydrogen might there therefore be lurking within reach beneath the Earth's surface?
The units that we refer to are million metric tons or megatons. And so we estimate that there could be anywhere from maybe just a few thousand of megatons to potentially billions of megatons in the Earth's crust. And the median or most likely value is on the order of around 5 million megatons. On the order of millions of megatons seems to be probably most likely.
And in energy terms, is that a meaningful amount? How would that relate to, for instance, the amount of energy that's locked up in natural gas that's exploitable at the moment?
The other thing that we have to be aware of is that this millions of megatons is actually for the entire Earth's crust. And so we make no prediction about the distribution of that hydrogen. And almost certainly most of this is going to be inaccessible. It's just simply going to be too deep or too far offshore or in accumulations that are much too small that they could never be economically recovered. But as a thought exercise, I say, well, let's assume that maybe if there is 5 million megatons in the subsurface, and if we could recover just, say, 2% of that, that would represent 100,000 megatons. And I did a quick calculation to see how much energy is in that. And it's roughly about twice as much energy as all of the proven reserves of natural gas on Earth. So it seems that if we could recover just a fraction of what we think is down in the subsurface, it could actually be a substantial amount of energy.
It sounds to me like you're saying that your predictions are the world actually is quite replete with hydrogen. But there's enormous uncertainty as to whether we can actually get at this, what would be a wonderful resource if we could access it. So is it even worth pursuing this, do you think?
From my perspective, the answer is clearly yes. I think it is, that there's enough potential here. And given what we know about other gases, about natural gas, about CO2, helium, hydrogen, it seems that it's quite likely that we could have accumulations of natural hydrogen in places that could be accessible and economically recovered. And the key point is that we just simply have never looked for it.
Sometimes we just don't realise what is literally underfoot, do we? That was Jeff Ellis, and that study detailing the discovery was just published in Science Advances.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound. Perfect music for audio and video productions.
This is The Naked Scientists with me, Chris Smith. Still to come, what have the Romans done for us? Well, maybe they knocked a few points off our and their IQ levels. We'll find out later. But first, researchers in London have found that prostate cancer that's become resistant to existing hormone therapies could be treated with an experimental new drug. It's called NXP800 at the moment, and it's currently in clinical trials for other cancers, including ovarian and bile duct tumours. It works by stressing out cancer cells to the point of killing them. Here's Adam Sharp, who's a co-author on the study and leader of the Translational Therapeutics Group at the Institute of Cancer Research in London.
Over the past 10 to 15 years, we've developed many treatments that can help control prostate cancer and allow men that have advanced disease, so that's disease that has spread beyond the prostate, live for longer. But the biggest challenge we have is that after time, sadly, those treatments stop working because the cancer becomes resistant to them. What it does is it learns ways to overcome the treatments that we're giving to our patients, and it stops working, and therefore the cancer continues to grow. So in this work, we were really trying to develop new treatments that work through new ways that could maybe help patients that other treatments had stopped working for.
I suppose it's a bit like when bacteria become resistant to antibiotics, isn't it? It's that they have evolved ways to surmount whatever the blockade imposed by the drug is. So how have you attacked this then? How have you gone after flushing out new avenues that will clog the works up and stop these cancers, even though existing treatments can't?
The cancer cells are very stressed, and they're stressed because they do grow uncontrollably. So what that means is the cancer cell needs to protect itself. And one way that it does that is it uses a particular family of proteins, the chaperones. They just really protect the cell from that induced stress that the cell is undergoing so that it survives rather than dies. And what we did in this study was we actually looked at a drug that had been discovered and developed here that really tries to stop these chaperones from working and increases the stress that the prostate cancer cell is under. And what we wanted to do was to actually decide if we were to give this drug to our cancer cells, would they be under so much stress that they no longer could survive, and actually they would either reduce their growth or even die. And that's what we really wanted to look at in this study.
How did you do it?
My colleague, Professor De Bono, has a huge number of patient samples. So we first wanted to ask the question, are these chaperones, so these molecules in the cancer cell, do they make the cancer cell more happy? So we actually identified that patients that have more of these chaperones in their cancer cells sadly did worse to current treatments. And then we wanted to take this drug to see whether or not it worked. It's meant to increase the stress or reduce those chaperone proteins that the cell likes to increase the stress. So we treated prostate cancer cells in our labs, and we also treated mini tumors that have come from prostate cancer patient samples. And these specific cancer cell samples were resistant to our current treatments. And what was exciting to see was that with this drug, these actual cancer cells started to die. Then what we did following that was we then tested it in animal models as well to show similar effects to what we were seeing in the lab cancer cells.
Effectively, you're robbing the cancer cells of a defense they rely on, so they become stressed to the point of toxicity. They just die. But what's to stop them just evolving a defense against the drug so they can switch those defenses back on, as it were, and just do what they've already done for the other treatments, and we're just kicking the can down the road a bit here?
Yeah, and I think that's a really important statement. The challenge, as you've said, is the cancer will evolve ways to overcome resistance to the new drugs that we're also developing. So alongside developing those drugs in themselves, we also now, following from this work, is start to look about what drugs could we put the new drug with, to maybe overcome the mechanisms of resistance that occur.
How selective is the drug for prostate cancer cells? Because obviously these proteins that you're robbing the cancer cells of play a really important role in protecting healthy cells as well. So are there not potentially really serious side effects from doing this?
Yes, I think again that's a really important question. The way that we would describe it is actually cancer cells themselves can become more sensitive to these treatments because they have more reliance on those chaperones. A normal cell that isn't as stressed doesn't actually require them as much as a cancer cell. And what we hope is that that's what can deliver us the therapeutic window.
Could this treatment also become a way to make other treatments even more effective? Because when you're treating prostate cancer with, for example, radiation, that's really stressing cells. So if you give a drug at the same time that makes them even more vulnerable, does that make the power of the radiation, the killing effect, even more potent? And therefore you could get away with, say, lower doses or get an even better response in the cancer so the person has a better outcome?
Fantastic question. I think that's what I actually hope more about this paper is not so much our work, but also bringing interest to the field. And there has been some great work from other labs that have already showed that targeting, increasing the stress response can sensitize to radiotherapy.
At the moment, you've done this in a dish and you've done it in these experimental animals. How close are we now to being able to do clinical trials? Do you foresee this being a relatively easy route into the clinic?
This work is done in preclinical models in the lab and is exciting, but of course, that's still a long way from showing that it works in prostate cancer patients in the clinic. What's exciting is the drug itself has been developed and it's now being given to patients with advanced ovarian cancer and cancer of the upper GI tract. And therefore, the clinical trials are already running. What I hope is also exciting enough about this work is that it will make our collaborators in biotech and industry start to think about prostate cancer as a potential another indication for this drug.
Great news. That was Adam Sharp, and that study has just been published in the journal Clinical Cancer Research. Now, if Monty Python's Life of Brian has taught us anything, it's that we have the Romans to thank for pretty much everything. But it seems it might not all have been entirely beneficial. Indeed, new research suggests that intense lead mining and processing at the height of the Roman Empire may have engulfed Europe in widespread pollution, which in turn contributed to the cognitive decline of the population, although not to the same extent as lead in petrol in the 1970s. Joe McConnell at the Desert Research Institute in Reno has been telling me all about his study.
I study ice cores. In this study, we used 3 ice cores, 2 from Greenland, from the Greenland ice sheet, and 1 from the Russian Arctic. And these were collected a long time ago, over the last 20 years, by many of my European colleagues. And we analyzed these in my laboratory at extremely low levels, but we can use those variations in those very, very low levels to look at changes in emissions of pollutants.
And how do you know when they relate to in time, these ice cores?
Yeah, it's a great question. We count annual layers in the chemistry. It turns out, in my lab, we measure about 30 different chemical species all at the same time, depth resolution. And so we can count, just like tree rings, we can count those annual layers starting at the top and just count them backwards thousands of years. And then we use things like known volcanic eruptions, and there happened to have been one in Alaska in the year 43 BCE that we can tie directly to the tree ring series and to all these different ice cores.
And what, the ice captures a snapshot of what the air was doing when that bit of ice got made at that particular point in time? Is that the rationale for doing this?
Absolutely. So there are these little things called aerosols, or little particles and droplets in the air all around us all the time. And they come from things like forest fires or pollution or volcanic eruptions, desert dust, sea spray, things like that. And those impurities are captured by falling snowflakes or by raindrops and deposited in the snow, or in this case, on the ice sheet.
And what does the lead footprint look like? Is it significant?
It's easily detectable. And one of the reasons that we focus on lead, besides the health implications, is that humans in their early mining and smelting created a lot or emitted a lot of lead. And so the background of lead in the natural environment is quite low. But humans, because of our mining and smelting, really put out a lot of it. And so the signature of human impact is quite clear in these ice cores in terms of lead.
And was it chiefly the Romans 2,000 years ago that were playing with lead? So you can say, well, it was them that have made the signature that you can see in these ice cores mapping onto that time point? Or were other humans around the place, other races, were they also using lead?
Historians and archaeologists tell us that the primary sources would have been the Roman Empire, and then there was quite a bit of activity in China. Using atmospheric models and then lead isotopes, the isotopes of the lead itself, we can evaluate where the lead must have been coming from. In this case, where these ice cores are located, the sensitivity of the ice, meaning how sensitive the ice core record is to emissions, is about 10 times greater for Europe than it is for China. So it's not impossible that we're seeing some lead from China. It's just that the emissions would have to be at least 10 times greater to equal the same amount of emissions from Europe. And then finally, we can use these isotopes. And what we find is the lead deposited in Greenland has a similar isotopic characteristic as the ore bodies in southern Europe.
And how do you then relate what the ice is saying was there to what the concentration for where the people were must have been in the air? So in other words, if you were a Roman, either living in a town or working in one of these settlements that was producing this, how much lead would you have been exposed to, do you think, based on what the ice is telling you?
Somewhat surprising for me, at least, was how widespread the pollution was. The atmospheric modeling suggests that it was basically extended over the entire Roman Empire. And that goes all the way from North Africa to what is now Germany and all the way over to the Black Sea.
How would that relate to if we wound the clock back, just say, 100 years? Because we were using a lot of petrol that was all leaded until into the 80s. We were all using leaded fuel because it was better for engines. So how would our lead pollution in that era compare with what the Romans were doing? Were we worse than them effectively, or not as bad?
No, we were definitely worse. The blood lead levels that would have resulted from this air pollution were about 3 times higher during the late 1970s, at least in the US, than they were during the Roman period. As you mentioned, lead has really been cleaned up in the last 20, 30 years, 40 years maybe, since passage of things like the Clean Air Act in the US and similar legislation around the world. And the Romans were experiencing about 3 times the exposure children today are experiencing.
But of course, children, when I was a child, were probably getting a much higher dose than a Roman child would.
Absolutely, and there was cognitive decline and other health impacts as a result.
And so we know that there are studies tying lead pollution to human exposure in the more modern era. So you can presumably back extrapolate that to what was going on in ancient Rome and try and make some kind of guesstimates as to what kind of impact it might have had on general health and cognition.
Maybe about 2.5 to 3 points. Keep in mind that the average IQ is 100. So that means you're dropping about 2 to 3% of your IQ. You might sound like a small number, but when it's applied to the entire population, I would think is pretty significant.
Absolutely fascinating. That was Joe McConnell, and that study has just been published in the journal PNAS. Now, before we go, we just have time for Question of the Week, and James Titko's journeying hundreds of millions of years back in time to answer this tectonic teaser.
Hello, it's Damien from Hathersage in the Peak District in the UK. My question is, if the continents were once all joined up as a supercontinent, what was on the other side of the Earth? Was it all just water? Thank you.
Thanks, Damien, for a brilliant question. If you go back 200 to 300 million years ago to the Permian and Triassic periods, fairly recent on geological timescales, believe it or not, most of the Earth's landmass was clumped together on one side of the planet, just as you point out. This is known as Pangaea and occurred by chance movements of the tectonic plates which make up the outermost layers of the Earth. Next time you look at a map of the world, look at the west coast of Africa and the east coast of South America. If it looks like they could fit together, it's because once they did. So naturally, on the other side of the globe to Pangaea was a vast global ocean known as Panthalassa. So what do we know about this huge body of water? Well, not an awful lot, since the oceanic crust underneath Panthalassa was largely subducted. This is a process whereby the denser oceanic crust slides underneath the less dense continental crust as tectonic plates drift into each other over time. This makes it harder for geologists to study. We can say more about Pangaea, where much of the supercontinent is known to have been arid. You can see the red desert sandstones deposited from this time in many places in the UK today. We can also say that the effect of having one huge ocean basin across much of the world, rather than the multiple smaller ones we see today, would likely have had a large bearing on deep sea circulation patterns, which are crucial to regulating the global climate and distributing the uneven balance of sunlight which strikes the Earth. That would account for the hotter summer, colder winters, and all-round dryness of much of Pangaea. To add to these hostile conditions, 250 million years ago, an eruption of huge volumes of magma in modern Siberia above a hot upwelling plume of material in the Earth's mantle made the Earth's climate extremely hot and unpleasant, and caused the biggest mass extinction in the Earth's history. Pangaea was eventually broken up by the continents moving apart, and one of the major boundaries along which this happened became the Atlantic Ocean, the second largest in the world today. I hope that answers your question, Damien. It was a really fun one to answer. Join us next time on Question of the Week when we're answering a new question.
Hi, it's Andrew in Cambridge. We have a holiday home in a French ski resort at 1,650 metres above sea level. And everyone who visits experienced, I'm going to call them high-definition dreams with much more detail than they normally experience when they're in Cambridge, 6 metres altitude. Does altitude affect dreams, and do mountaineers who go much higher notice the same effect?
And we'll look forward to the answer to that one. Thank you very much, James. In the meantime, if you think you know the answer, you can have your say, of course, on our forum. That's at nakedscientist.com/forum. You can also drop us a line with both answers, but also new questions for us to consider. The email address chris@thenakedscientist.com. Now, at this point, it falls to me to say that if you enjoy the programmes that we make for you, do please try and help us out with a donation to support the show. We rely very heavily on the generosity of you, our listeners, to meet our running costs, and it is a huge boost to us and for us when you help us. I personally write back to everyone who does help us out to say a big thank you. You can join in, and please do, by going to nakedscientist.com/donate. We've made it very easy and very secure. nakedscientist.com/donate. Thank you. And that is where we have to leave it for this episode, but do join us on Tuesday when Titans of Science continues with deep sea microbiology expert Antje Boutius. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.